Welcome to Maxwell's Equation Review Lecture 9.1. What we're going to do is going to be talking about Maxwell's equation. Okay, so we have Gauss's law for magnetic fields. And this is for Physics 222, that is calculus-based students. If you are an algebra-based student, please skip ahead to slide number 11. You're welcome to stick around if you want to, but if you have not had calculus, it probably won't make much sense. So skip ahead to slide number 11 if you don't have calculus. If you do, this is where you begin on slide number 2. Okay, so Gauss's law for magnetic fields is a formal way of saying that magnetic monopoles do not exist. The law asserts that the net magnetic flux phi b through any closed Gaussian surface is zero. That is, you cannot enclose an individual magnetic pole. Now, if you look carefully here, here's an enclosed surface. It supposedly encloses this north pole, but look, there's as many field lines coming in as leaving. Okay, so in other words, the net is zero. That's out minus in. If out and in are equal, then the net is zero. And this is what this says. Phi b equals the integral over the entire closed surface of b dot dA, and that has to equal zero because you have as much flux coming in as you have leaving. Okay, Gauss's law, you can enclose a single charge. If you enclose, for instance, this surface 1 here, everything's leaving. So there is a net Q enclosed here. And that's not equal to zero. It can be if you enclose like this surface here, okay, but it's not. But then, of course, you've got a positive and negative charge, and they cancel each other out if they're equal. So phi equals the integral over the entire surface of E dot dA, and that equals Q enclosed over epsilon naught. Now, these two are different. Now, if we ever do find magnetic monopoles, there would be a non-zero term over here. But so far, I've been waiting. Nobody's done it yet. Again, this is Physics 222. Ampere's law says the integral of B dot ds equals mu naught I enclosed. This gives the magnetic field generated by a current I enclosed encircled by a closed loop. Faraday's law says the integral of V dot ds equals minus d phi b dt. That gives the EMF for the electric field created by a changing magnetic field. Now we know from experiment that electricity and magnetism are closely linked. Currents are produced by electric fields and they produce magnetic fields. Symmetry is always a very powerful concept in physics. So it's natural to ask if a changing electric field can produce a magnetic field. Maxwell realized that it does and that there was something missing, and he was the one who completed the symmetry. And for that, we honor him. Ampere's law, the integral of B dot ds equals mu naught I enclosed, gives a magnetic field generated by a current I enclosed piercing a surface bounded by a closed loop. We're going to apply Ampere's law to a charging capacitor. Surface 1, there is no problem. There's a current in the wire that pierces the surface bounded by the loop and generates a measurable magnetic field around the wire. We're also free to take a surface parallel to and between the plates bounded by a closed loop centered on the capacitor's central axis. Now, no current pierces this surface, and yet we detect a magnetic field as long as the capacitor is either charging or discharging. In other words, the magnetic field exists as long as the electric field inside the capacitor is changing. Now, there is no current going through here. It's just a changing electric field. Maxwell fixed this situation by imagining a displacement current that was created by the changing electric field. ID equals epsilon naught d phi e dt. Now, remember, phi e is E times A, and what's changing in here is the electric field, not the area. So it's ID equals epsilon naught A dE dt. Ampere's law, which says the integral of B dot ds equals mu naught I enclosed, gives a magnetic field generated by a current I enclosed encircled by a closed loop. Maxwell's idea is that ID equals epsilon naught d phi e dt. When you're charging or discharging a parallel plate capacitor, Q equals epsilon naught A times Z, and the charging rate is equal to the current, which is, of course, dQ dt, and that equals epsilon naught A dE dt. Assuming an ideal capacitor with a uniform electric field, ID equals epsilon naught d phi e dt, and that equals epsilon naught dEA dt, and of course the area doesn't change. So this ID equals epsilon naught A dE dt. If we compare this equation with that equation, we see they're exactly the same. So ID is, surprise, 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 just the current that's charging the capacitor. Okay, so this solves the mystery. Ampere's law gains a new term, becomes Maxwell's law, because he completed the symmetry. And the full law is the integral of B dot ds equals mu naught times this quantity, I enclosed, plus epsilon naught d phi e dt. When the capacitor is being charged and the electric field is changing, there's a magnetic field around the wires and also one that is around the capacitor and between the plates too. So a changing electric field creates a magnetic field. Furthermore, Maxwell realized that the changing electric field induces a changing magnetic field, which induces a changing electric field, etc. We call this magic electromagnetic radiation, otherwise known as light. And if you haven't yet thought about this, take a few seconds to think of how important this is to you. Okay, so yet another right-hand rule. However, in reality, it's just kind of a variation on an old friend. So for a surface S bounded by a closed curve C, we choose either the clockwise or the counterclockwise direction around C. You curl the fingers of your right hand around the curve in the chosen direction, with your thumb perpendicular to the surface. Your thumb then defines the positive direction. A flux phi through the surface is positive if the field is in the same direction as your thumb, as negative if the field is in the opposite direction. A current through the surface in the direction of your thumb is considered positive, and the direction opposite your thumb is negative. Now, the way I handle this is I always put my thumb in the direction of the current or the direction of the electric field. And of course, those are the same direction because remember, the current is a flow of hypothetical positive charges, and positive charges swim downstream in electric fields. So in other words, the current is in the same direction of the electric field. If you put your thumb in the direction of the current or the direction of the electric field, you will always have a defining positive. Okay, and that also tells you the direction of the magnetic field created by either that current or the changing electric field between the plates of the parallel plate capacitor, or any changing electric field. Think back, remember the one that we had for finding the direction of the magnetic field around a current carrying wire. You grab the wire with your thumb in the direction of the current, which is also the direction of the electric field in the wire, and your fingers curl in the direction of the magnetic field created by that current. This is the same rule we had before, so it's nothing really new. It's just a slight expansion on what we had before. Now, this is only for calculus-based students. Magnetic field induced by capacitor changing electric field. A parallel plate capacitor with circular plates of radius big R is being charged by a current little I. Between the plates, what is the magnitude of the integral of B dot ds in terms of mu naught and I at a radius little r equals to R over 5? So in other words, you're 1/5 of the way out from the center of this parallel plate capacitor. We're going to find out what is the magnitude of the integral of B dot ds there. In terms of the maximum induced magnetic field, what is the magnitude of the magnetic field induced at that point inside the capacitor? The physics of this is Maxwell's law of changing electric field in parallel plate capacitor. Okay, so we write down everything we know, known and unknowns, and we know that little r is big R over 5, and we're looking for B max, what it is in terms of B max. The formula is the integral of B dot ds equals mu naught ID enclosed. And ID enclosed is just basically proportional to the area that's enclosed because it's a uniform field. The bigger the area you enclose, as long as you're between the plates. And we're not talking about when you get outside the plates, just between the plates. So it's proportional to the area that's enclosed. And of course, the area is just pi times little r squared. That's for inside the plates. B then becomes mu naught ID divided by 2 pi r big R squared times little r. Okay, we'll see that in a minute. Okay, so the integral of B dot ds equals mu naught ID enclosed. ID enclosed divided by ID is just the area enclosed divided by the total area of the plate. And that is just pi little r squared divided by pi times big R squared. So ID enclosed is just ID times little r squared divided by big R squared, where ID is the total one. Okay, so then the integral of B dot ds equals mu naught ID times little r squared divided by big R squared. And of course, little r in this problem is 1/5 of big R. So that's where this comes from. These two r's will cancel out, and the phi squared is 25. So the integral of B dot ds equals mu naught I over 25. That's at this point where you're 1/5 of the way out from the center to the edge. Okay, now B max, if you do this all the way out and applied it all the way to the edge, B max is mu naught ID divided by 2 pi times big R squared times R. And at R equals big R, B max is just mu naught ID divided by 2 pi r because one of them cancels out. And of course, that is right at the edge here. Now that is where you enclose the maximum amount of displacement current, or in other words, the maximum amount of electric field. So then B is written for any R inside the parallel plate capacitor as mu naught ID divided by 2 pi big R squared times little r. That's for R inside between the plates. Okay, and of course for r equals big R over 5, this becomes mu naught ID times big R over 5 divided by 2 pi r squared, and of course this becomes mu naught ID divided by 10 pi r, or 1/5 B max, which makes sense because it goes as R. So this is what it looks like inside. This is the edge. You get the maximum field right at this edge here, which makes sense because you've enclosed the maximum amount of electric field there, or maximum amount of displacement current, however you want to look at it. Okay, remember displacement current is kind of imaginary, but it's equal to the current that is charging the capacitor. When you get outside, okay, the enclosed stays the same once you get beyond this edge. So then it falls off as 1 over R, just like it did outside a long wire. Okay, so these are basically the same equations for a current carrying wire, and that makes sense. So outside the parallel plate capacitor, magnetic field falls off as mu naught ID divided by 2 pi times the quantity 1 over R. So that's this part of the curve. Now, just like anything else, it has to make sense. Okay, Physics 122 students here, come here. If you are a Physics 222 student, unless you want a non-calculus-based review, okay, you will go to slide number 15. Okay, for 122, which is algebra-based, Ampere's law states that the sum, roughly the sum of B parallel delta L is approximately equal to mu naught I enclosed. This gives a magnetic field generated by a current I encircled by a closed loop. Faraday's law says that the sum of E parallel delta L is approximately equal to minus the time rate of change of the magnetic flux. This gives the EMF for the electric field created by a changing magnetic field. But we know from experiment that magnetism and electricity are linked. Currents are produced by electric fields and produce magnetic fields, and symmetry is an extremely powerful concept in physics. So it's natural to ask if a changing electric field can produce a magnetic field. Maxwell realized that the answer to that question was an emphatic yes, and he also realized that that meant there was something missing, and he completed the symmetry, which is linking these two. Okay, at this point, Maxwell realized that something was missing. He knew Ampere's law, which is summation of B parallel delta L equals approximately equal to mu naught I enclosed, gives a magnetic field generated by a current I enclosed that's piercing a surface bounded by a closed loop. So we're going to apply Ampere's law to a charging capacitor. For surface 1 here, there's no problem. There's a current in the wire that pierces the surface bounded by the loop and generates a measurable magnetic field around the wire. We can also take a surface that is parallel to and between the plates, bounded by a closed loop that is centered on the capacitor's central axis. No current pierces this surface, and yet we detect a magnetic field as long as the capacitor is either charging or discharging. In other words, the magnetic field exists as long as the electric field inside the capacitor is changing. Maxwell fixed this situation by imagining a displacement current that is created by the changing electric field. And this displacement current is ID. ID is approximately equal to epsilon naught delta phi E delta T. Okay, so now we've got these two ideas. And now we had to bring them together to complete the symmetry. So when charging or discharging a parallel plate capacitor, Q is just epsilon naught A times E, and the charging rate is equal to the change of Q with respect to T. And if we do that, the current is just epsilon naught A delta E delta T. If we assume an ideal capacitor with a uniform electric field, ID is then equal to epsilon naught delta phi E delta T, and of course phi E is just E times A. A doesn't change, we can pull it outside. So ID equals epsilon naught A delta E delta T. If you look at these two equations, they're the same. So ID equals I. So this gives Ampere's law a new term, and we call it Maxwell's law. I like to call it Ampere-Maxwell. I don't just give one person credit, because it's just like building a house. Okay, Maxwell completed the house, Ampere built the foundation. And you can't have a house without a foundation. It doesn't work very well. Okay, not if you want something that's permanent, it's going to last any time. So Ampere's law gains a new term, becomes Maxwell's law, because he completed symmetry, but I call it the Ampere-Maxwell law. Sum of B parallel delta L is approximately equal to mu naught times this term, I enclosed plus epsilon naught delta phi E delta T. Okay, so when the capacitor is being charged and the electric field is changing, there's a magnetic field around the wire, some plus ones around the capacitor and between the plates too. So a changing electric field creates a magnetic field. Furthermore, Maxwell realized that a changing electric field induces a changing magnetic field, which induces a changing electric field, and these two fields make a combined wave that travels at the speed of light that we call electromagnetic radiation, otherwise known as light. Because if you think about this, The only wave that travels through the vacuum of space is light, electromagnetic radiation. And without that, the Earth, we wouldn't have sunlight, because that's how the sun's warmth and light reaches us. It's through electromagnetic radiation. The Earth would be a solid frozen ice ball, and we wouldn't be here. Okay, so an induced field, an increasing solenoid current causes an increasing magnetic field, which induces a circular electric field. So here you are, you're increasing the current in here, and this causes this magnetic field to build up, and that will induce a circular electric field. Faraday's law describes this. An increasing capacitor charge, and these two are kind of pretty much the same thing. One deals with magnetic fields, the other one deals with electric fields. And that's where they store their energy. See, it's always about energy, because that's what an electromagnetic wave is. It's just a transport of energy from one place to another, and it's very efficient. An increasing capacitor charge causes an increasing electric field, which induces a circular magnetic field. And there's kind of a right-hand rule for this, by the way. If you take your thumb in the direction of the electric field, which would be, if this were a current, the electric field would be pushing the positive charges. Remember, positive charges swim downstream? And remember, we always call it conventional current, which is the directional flow of hypothetical positive charges. And that would be along, in this case, into the page, in the direction of the electric field. And look which direction your fingers are going. They're going in the direction of the induced magnetic field. It's the same right-hand rule that we had for figuring out the magnetic field around a wire. You grab the wire with the thumb pointing in the direction of the current, your fingers point in the direction of the magnetic field around the wire. It has the same rule and the same magnitude, too. Okay, so here's all of Maxwell's equations. This is the electric and magnetic fields are described by the four Maxwell's equations. Why do we name them for him? Okay, and ignore all these other guys? Well, we don't. They're there, too, because they all have credit. But he was the one that did this. He brought all of this together. So this is basically why we honor him, because there's nothing higher in physics than to bring everything together and put it onto one simple thing. The integral of E dot dA equals Q enclosed divided by epsilon naught. That's Gauss's law. The integral of B dot dA equals 0. That's for magnetism. This means there's no magnetic monopoles. The integral of V dot ds equals minus the time rate of change in the magnetic flux. Gives you the electric field. Here is the integral of B dot ds equals mu naught times the quantity I through, that's the I enclosed, through the surface, plus epsilon naught d phi e dt. So here's the changing magnetic field creates a changing electric field, and here's the changing electric field creates a changing magnetic field. That's electromagnetic radiation. So that's let there be light. Okay, and here's another thing here. Now, this is just basically superposition. If you are Physics 122 students, don't be too worried about this. Just listen to the general idea here. Okay, so in addition to Maxwell's equation, which describes the field, a fifth equation is needed to tell us how matter responds to these fields. This is both the magnetic and the electric forces. We've done these separately, but now we're going to put them together. Force is equal to Q times the quantity of E plus V cross B. So this is the electric force on a charged particle. This times Q is the force on a moving charged particle from the magnetic field. So again, this combines the electric forces with the magnetic forces on moving charges. This unifies electricity and magnetism and leads us to this neat device called a railgun. Okay, I'm going to put this on this, and there you go. Notice how that is going so fast when they fire these things, especially large ones. These things move so fast, they're like meteors. They set the air on fire, okay, from just the friction alone from the air, from the drag forces from the air. They set the air on fire. Now, the cool thing about this is the Navy wants to use these for ordnance. So here we have the 5 fundamental ideas of electromagnetism. Gauss's law says charged particles create an electric field. Faraday's law says an electric field can also be created by a changing magnetic field. Gauss's law for magnetism says that there are no isolated magnetic poles. The Ampere-Maxwell law says currents create a magnetic field, and magnetic field is created by a changing electric field. Lorentz force law says an electric force is exerted on a charged particle, electric field, and a magnetic force is exerted on a charge moving in a magnetic field. So these together are the 5 fundamental ideas of electromagnetism. And this is the final point where we're now going from electricity and magnetism, and now we've unified them, and the rest of the course will be electromagnetism and optics. And then finally, we'll talk about relativity. which has to do with the speed of light. Nothing can travel except for Carol with a cup of coffee. Nothing can travel faster than the speed of light. Okay, at this point, if you are Physics 122 students, that is algebra-based students, you're at the end of this lecture. Thank you. If you are a calculus-based student, that is Physics 222, press on. We have a few more slides for you. Okay, now this is on determining the direction of the displacement current in the resulting magnetic field. Again, this is only for calculus-based students. The induced current is ID equals epsilon naught d phi e dt, which, if the area is fixed, and assuming like it's a parallel plate capacitor, that equals epsilon naught a dE dt. Since it's the change of the electric field with respect to time, the direction of the change matters. If it's an increasing electric field, that is charging a capacitor. If the electric field is increasing, then ID, which is epsilon naught d phi e dt, is greater than 0, and then ID is positive. The direction of the displacement current is the same as the direction of the electric field then. The right-hand rule for this is the thumb is in the direction of the positive current, which is in the same direction as the E field. The fingers curl in the B field's direction. If it is a decreasing electric field, that is maybe a discharging capacitor, if the E field is decreasing, then ID, which is epsilon naught d phi e dt, is less than 0, and ID is negative. The direction of the displacement current is opposite the direction of the electric field. The right-hand rule for this is that the thumb is in the direction of the positive current, which is in the opposite direction of the electric field. So the fingers curl in the B field direction. So here's some strategy for this. You look at the direction of the electric field. Is it changing? If the answer to that's no, you don't have to worry about it because ID is 0. If it is changing, then you have to ask yourself, is it increasing, that is charging a capacitor, or decreasing, such as it discharging in a capacitor? If it's increasing, increasing equals same. If it's increasing, then your thumb and the displacement current point in the same direction as the electric field. If it's decreasing, decreasing is opposite. If it is decreasing, then your thumb and the displacement current point in the opposite direction of the electric field. Your fingers curl in the direction of the magnetic field. So here's some examples of this. Example 1, we have electric field into the page, and it's increasing as in a charging capacitor. ID, which is epsilon naught d phi e dt, is greater than 0, so ID is positive. The thumb is in the same direction as the electric field, so it's also into the page. The fingers in the magnetic field. If you try this, put your thumb into the page, try it right now, and fingers curl clockwise. Example 2, the electric field is out of the page and increasing as in a charging capacitor. ID, which is epsilon naught d phi e dt, is greater than 0, so it's positive. The thumb is then in the same direction as the electric field, so it's also out of the page. And you point your thumb out of the page, your fingers and the magnetic field will curl counterclockwise. And you'll get the test question right. Okay, example 3, the electric field is into the page and decreasing as in perhaps a discharging capacitor. Then ID, which is epsilon naught d phi e dt, is less than 0. In other words, it's negative. The thumb is in the opposite direction of the electric field, so the thumb is out of the page. And if you try that, you'll find out that your fingers in the magnetic field curl counterclockwise. Example 4, the electric field is out of the page and decreasing as in a discharging capacitor. ID, which is epsilon naught d phi e dt, is less than 0, so it's negative. So the thumb is in the opposite direction as the E field, so the thumb is into the page. If you try that, your fingers in the magnetic field curl counterclockwise. Thank you.